Hello and welcome back to your Chem 4 lecture. We are starting lecture 5 today, which is going to wrap up chapter 3. Remember, we were talking about matter in the previous one, and now we're going to talk about the other part that's going to explain why things look the way they do on the macroscopic scale, which is energy. And if we have a good understanding of matter and energy, then we're going to have a good understanding of why matter behaves the way that it does. So real quick, energy, of course, is a word that you've heard before, and you probably have some understanding of sort of the common way that we refer to energy. In science, there's a very technical definition, and energy is the ability to do work. And if you've taken a physics class, you'll know that work is like a force that's applied across a distance. So the simple example is like pushing a box across a floor. You're applying a force over a distance, and that is work that you're doing. Now, that's not the only thing, right? You can also, like, when you lift up a pen, for example, you are applying a force to pull that pen up against the force of gravity. So you're applying a force, again, across the distance. We also have two different types of energy that we're going to kind of classify here. We have kinetic energy and potential energy. Potential energy, pretty straightforward. This is stored energy. So, for example, if I go to my pen again, if I lift my pen in the air, the pen now has potential energy due to its position. In other words, if I were to drop the pen, then the pen falls to the floor. Now, that's an example of the potential energy that I had up here turning into kinetic energy, which is the energy of motion. The kinetic energy is basically any motion that you detect is a form of kinetic energy. So it's like energy as it's being used is the way that you can think of it. Again, the falling pen is an example, running around, kicking a ball. All of these things are kinetic energy. So another example, a useful way to think of potential versus kinetic energy is to think about a dam. So water that is behind a dam has potential energy. If the dam releases that water, the water flows over the dam, the potential energy is then converted into kinetic energy. So what was potential energy from the dam holding back the water, where it wants to, of course, flow to the lowest point, when the dam's released, now that water is moving, right? That's motion. So that's kinetic energy. Okay, so let's go ahead, identify the energy in each of these as either potential or kinetic. This is in your sample exercise packet, which is posted below the lecture slides. So go ahead and check this out for sample exercise number 5. And pause the video now, and we'll go over it here in just a second whenever you're ready. Let's go ahead and take a look. So rollerblading, of course, you're moving, that's kinetic energy. A peanut butter and jelly sandwich. Now, I guess I didn't do a good job explaining this here, but food that you eat has potential energy as well, stored in its chemical bonds. You can access that potential energy by eating it, and then your metabolism will rip apart the bonds and take the energy out of it, and then you can turn it into kinetic energy. Sorry, I should explain that a little bit better. When you mow the lawn, that's you have the blades going around. That's an expenditure of kinetic energy. And gasoline as well, just like the food. Gasoline is like food for your car, right? Your car burns the gasoline, and in so doing, it takes the energy that's stored in the chemical bonds that are in the gasoline and turns it into kinetic energy. So yeah, I did a bad job explaining that before. Did I miss something? Yeah, the chemical composition of an object can give you potential energy as well. Let's see here. So, okay, we'll talk about the units for heat next, which for the SI system, the SI unit is the joule, spelled here, capital Joule, and then S. This is a guy's name. That's why it's a different. That's why it doesn't really make any sense. A lot of these SI units were named after different people. Famous scientists got their names kind of immortalized in these units. So heat, when we talk about heat, what we're doing is we're talking about the energy that's associated with the motion of particles in a substance. So when you think about something that's hot versus something that's cold, um, for example, ice water versus, let's say, boiling water. Of course, they're both made of water, but we definitely would notice the difference if we were to plunge our hand into the boiling water or into the ice water. The difference is the motion of the molecules in the water samples. In a hot water sample, the molecules are moving very, very fast. In an ice water example, they're moving very slow. And that's something that we can feel because we maintain a homeostasis, right? There's a temperature that we are comfortable at, like 37 degrees Celsius or 98.6 degrees Fahrenheit. And if we plunge our hand into cold water, heat is released from our hand into the cold water. So we notice that we're losing heat, so it feels cold. The opposite is true when we were to plunge it into the boiling water. Don't try this at home. Please don't do this at home. I'm just giving you an example. Hopefully this makes sense and it's not something that you're going to try necessarily. Think of hot tea. How about hot tea? You take a sip of hot tea and you notice, oh, my tongue is hot. Okay, what's happening there? Well, the particles in the tea are moving faster than the particles on your tongue. And so some of that energy, as the particles in the tea collide with the particles on your tongue, is released into your tongue. And our bodies physiologically feel that as heat. So the idea is here basically the faster that particles move, the greater the heat or the thermal energy of that substance is going to be. We're going to use joules for our heat units, as well as energy and work. And of course, 1 kilojoule is equal to 1,000 joules. That's just like any metric unit, right? Okay, just to give you an idea of the like the amounts of energy. So like, what does a joule mean? Like, what does it mean in terms of like things that we use every day? So when you go to sleep for an hour, your body uses about 10 to the 5th joules. Okay. For energy that you would get from a serving of pasta, like a carb or something like that, or if you're going to bicycle for 1 hour, it's about 10 times as much. That's 10 to the 6th. 1 gallon of gasoline contains 10 to the 8th joules. Each person then in the United States uses 10 to the 11th joules. Note, this is a logarithmic scale, right? So each person uses the equivalent of 1,000 gallons of gasoline, right? 10 to the 3rd more gasoline energy than from 1 gallon of gasoline. In 1 second, the amount of solar energy that reaches Earth is 10 to the 17th joules. Compare that to the total energy consumption, and we're talking like electricity and transportation and all of that, not like individual personal consumption. Energy consumption for 1 year is about 10 to the 20th. So if it would take about 1,000 seconds of solar energy reaching the Earth, if we were able to harvest all of that, that would cover us for the whole year, at least in the United States, I suppose. So I think we got to do this for the world next. If we compare that to the world reserves of fossil fuels that are in the ground, it's 10 to the 23rd. And then compare that to, and that's if we could get them all out, obviously, that's which is physically impossible. And then as far as we and then finally, if you were to look at the sun radiates 10 to the 26 joules in 1 second, and that's in all directions, obviously. Okay, so now we use joules for our SI unit, and that's what we're going to use most commonly. But there's another unit of energy that we're going to be more familiar with, which is the calorie. Now, I want to point out here that the calorie that we're going to use here is not the same as the calorie that you see on the back of your nutrition chart or something like that. That's a little different that we're going to talk about on the next page here. But a calorie is a very useful unit. It's the amount of energy that's needed to raise the temperature of 1 gram of water by 1 degree Celsius. And it's defined as 4.184 joules. So 1 calorie equals exactly 4.184 joules. Okay, that gives us our conversion factors, right? 4.184 joules per 1 calorie and vice versa. Now, 1 kilocalorie, this is kind of useful unit here, is equal to 1,000 calories as before. And this kilocalorie here, sorry, there's actually two ways to write it. So let me get the notes up here. Very confusingly, this kilocalorie here, that is equal to our calorie, or what we call the nutritional calorie. Okay, and there's another way that we can see it here, which is this capitalized C. Because we have the capitalized C here, that tells us that we're talking about kilocalories, not the scientific calories. I know that's really confusing, and I apologize. I didn't come up with it, right? It just is the way that things have been for 50 or 60 years now. So apologies on that. I think they just didn't want to use kilocalorie because it's, I know it sounds like a lot, but you know what that is all about. Okay. How many okay, so here's sample exercise number 6. We'll do this one. Again, if you feel confident about your conversions, you can just go ahead and do it now. But if not, I'll be here and we will work through this one together. I guess I'm gonna have to actually go get my calculator. I don't know where I put it, but I'll go grab my calculator. But let's walk through it first. How many calories are obtained from a pat of butter if it provides 150 joules of energy when metabolized? So again, if you feel confident about your conversions using the conversion vectors we just saw, pause the video now and we'll have the answer up when you come back. If not, we can walk through it together. So how are we going to do this? Well, let's write out our solution, right? So we're starting from joules. And we need to convert that into calories, lowercase calories. Oops, calories. Okay, calories. And what's our conversion factor for joules to calories? Well, remember, it's 1 calorie per 4.184 joules. Okay, so let's go ahead and try the math. We have 150 joules times 1 calorie divided by 4.184 joules. And then we're ready to do the math. Okay, so I don't have my calculator here, but actually I think I have the answer on the next slide. So let's just kind of go through it here. So again, this is just showing what we just did here. You end up with 150 divided by 4.184. Now, whatever number you get in your calculator, remember, the 150 is a measurement. So you have to keep in mind your significant figures. 150 has 2 significant figures. The conversion here we said was exact. So that means our answer has to have 2 significant figures, which should be 36 calories. Okay, so now let's go ahead and talk about how energy relates to nutrition. I already mentioned the nutritional calorie, and we're going to talk about that here again. But we want to understand how energy works in the body. Now, at the end of the semester, we've got chapter 18, which is on metabolism. We'll actually see how chemical compounds are broken down, like carbohydrates are broken down in the body, basically, and how we get energy from there. But from now, we're just going to have kind of a bird's eye, very, very top level view of it. So carbohydrates are the primary source of energy because they're the easiest to chew up and get energy from. When we exhaust our carbohydrate reserves, then fats, which are long-term energy storage, will be metabolized. And then finally, proteins, proteins that make up the muscles, for example, will be used for energy. Okay, I already mentioned this, right? We have the nutritional calorie, that's the capital C, and that is equal to 1 kilocalorie. Again, apologies. Most other countries other than the United States are going to use kilojoules. So just keep that in mind. So here is, so here is, I think this is like from Canada or some country where they use both. There's the calories and kilojoules both listed in the nutrition label. Okay, all right. So you might ask yourself, now how is it that we actually get these calorie numbers for our food? Well, what we use is we use something called a calorimeter, which of course means calorie measuring device, right? Calorie measuring tool. What it actually is you take a sample of food and you provide a bunch of oxygen, because what you're going to do is you're going to burn your food sample. And as you burn your food sample, it's in this little container that's all walled off, so nothing else can come in. It's surrounded by water, okay? And this water is basically just going to absorb the heat that's released from the combustion of the food. And over here, we have a thermometer sticking in so that we can measure the temperature from this combustion. So this is for like specific foods. This is how you have to get those calorimeter, how you get those calorie values. So the typical energy values for food are given here. We've got carbohydrates, which are 4 kilocalories per gram or 17 kilojoules per gram. Fats, which are 9 kilocalories per gram or 38 kilojoules per gram. And then proteins, which are 4 kilocalories per gram and 17 kilojoules per gram. So in order for us to figure out the calories of a typical food, what we can just do is, if we have the grams of carbohydrates in the food, we can take the grams times 4 kilocalories per gram to give us the answer. Same thing with the kilojoule per gram conversion as well. If we know the grams of carbohydrates, grams of fat, grams of protein, we just multiply it by that conversion to give us the kilojoules. Okay, so here are some examples. I will only walk through a couple of these, but an apple is made up almost entirely of carbohydrates. So it's basically 15 grams of carbohydrates. Now, if you do the 15 grams times 4 carbohydrates per gram, you would end up with 60 kilocalories. I'm sorry, I said that wrong, but you get the idea. It's 4 kilocalories per gram of carbohydrate, and the similar conversion for kilojoules. Anything else that's interesting here? Beef as well. So beef has about 14 grams of fat and 22 grams of protein in a 3-ounce serving. And that adds up to about 220 kilocalories. When again, you take the fat times that conversion factor, plus the protein times that conversion factor. Now, a typical energy requirement is going to vary depending on a lot of different factors for adults. So note that we have splits here, like based on gender, for example, as well as age. Basically, these are like very, what do I want to say? They're very inexact. The real energy requirement is going to vary a lot for the type of adult that you are. Like for me, for example, like I'm pretty sedentary, so I don't actually need the 2,700 kilocalories per day, for example. Another thing is the way that a person would lose weight is if their food intake energy is less than the energy that they output, right? So sleeping, sitting, walking, sleeping and sitting, very low energy usage. Compare that to walking, swimming, running. You get a lot more calories used up when you do that, or more energy that's used up. And again, these are just typical values, just given to kind of show you an example. Okay, now the reason that we can use, so if we're going back here, I told you something back when we were looking at this calorimeter, which is that we burn the substance and we then measure the temperature difference for the water. And the thing about water, and really any pure substance, is that if you heat up a substance by a certain amount of heat, so joules, let's say, in other words, you add a certain number of joule energy to a certain sample of a compound, you can predict how much its temperature is going to rise. And this gives us the idea of specific heat. So specific heat, which is abbreviated as capital S, capital H, will be different for different substances, right? But it is defined as the amount of heat that's needed to raise the temperature of exactly 1 gram of a substance by exactly 1 degree Celsius. And this is, again, something that you've known as like practical knowledge for a long time, even if it doesn't really, even if you don't really think about it. For example, like if you're going to go cook, right? I guess I always bring stuff back to food, but this works out. So if you're going to cook, let's say you're going to cook, let's say you're going to make like a grilled cheese sandwich, and you're going to make macaroni and cheese, lots of cheese in this meal for some reason. When you go to heat up the pan that has that you're going to use for the grilled cheese, it's just an empty pan. When you go to heat up the pot for the macaroni and cheese, there's a pot that's filled with water. Which one's going to heat up faster? Well, you probably know that the pan that's empty, in other words, just has air in it, is going to heat up much, much faster than the pot that has all the water in it. And the reason is water has a very high specific heat. In other words, it has a high amount of heat that's needed to raise its temperature for every 1 gram by, whatever temperature that it is that you're raising it by. In fact, the specific heat of water is about 10 times greater than the specific heat of most metals. So the way that you calculate this, you take specific heat, that's what we're trying to calculate here. It's equal to the heat that's added to the system divided by the mass of whatever object it is or whatever substance that we're heating, and the change in temperature for the substance. This gives us units of joules per gram degree Celsius, or if we're using the metric system, that's calorie per gram degree Celsius. For water, water is a special a substance. As always, water is going to come up again and again as one of these kind of special chemicals because it's so important to biology, and for us just to live, we need water. And the specific heat for water is 1.00 calories per gram degree Celsius, which works out to 4.184 joules per gram degree Celsius. Okay, so let's go ahead and give an example problem for this one here, which is sample exercise number 7. I know sample exercise number 8 also deals with specific heat, so I'd like to just walk you through this one because I know it's not just enough to tell you, oh, the specific heat equals the heat divided by the mass times the change in temperature. Let's actually look at a problem, and then let's solve it together. If you feel confident that you can use it, definitely by all means pause the video, work out the problem. But if not, I totally understand. So let's go ahead and walk through this. So sample exercise number 7 says, what is the specific heat if 24.8 grams of metal absorbs 275 joules of energy and the temperature rises from 20.2 degrees Celsius to 24.5 degrees Celsius? Okay, so a couple of things we note about this problem right away. It's asking for the specific heat. Okay, well, we know that the specific heat, that's going to be not a conversion problem, right? This is going to be an equation problem. And we know that it's going to be equal to the heat that's divided by, and then divided by the mass and the change in temperature. So real quick, delta often means change in. So that's why we use this as like a kind of abbreviation here, change in temperature. And then mass, of course, is like in grams. Okay, so then what do we know? Well, we're given the heat, right? It says that it absorbs 275 joules of energy. So that tells us that we absorbed 275 joules. Great. The mass, that's also given to us here, right? 24.8 grams. So that's going to be 24.8 grams down here. And how about the change in temperature? How do we define the change in temperature? Well, the change in temperature is the final temperature minus the initial temperature. That's how I would write that out in mathematical terms. So the final temperature was 24.5 degrees Celsius. The initial temperature, 20.2 degrees Celsius. Okay, and then if we do all that math, that should give us 4.3 degrees Celsius here, which we're going to use up in here again. So that's 4.3 degrees Celsius. So with all of that, we have the heat, we have the mass, we have the change in temperature. So that should be that should give us our specific heat. Now again, I don't have my calculator, but I think I have this solved on the next page. Yes, okay, good. So we give the given and needed quantities. Okay, here's where we go. Specific heat equals the heat divided by the mass and the change in temperature. It's 275 divided by 24.8 divided by 4.3. And that gives us our final answer of 2.6 joules per gram degree Celsius. A note on putting this into your calculator, if this helps out, what you have is you have your numerator, 275, and then you're divided by 2 different things in the denominator. So I would put this in my calculator as 275 divided by 24.8, and then divided by 4.3. Now it's also correct that you could say 275 divided by, and then in parentheses, multiply these 2 numbers together. But that does use the parentheses function on your calculator. And I just find it to be pretty inconsistent. So again, I just recommend 275 divided by 24.8 divided by 4.3. Again, if you have any problems with that, make sure to see me during class and I'll show you how to enter it on the calculator in person. Okay, so here we go. So yeah, some examples of specific heats. I already mentioned that these metals are, oh, I might as well tell you this now. So you're for sure going to see a problem like this on the exam. And I love this type of problem. And what I'm going to do as well is I'm going to give it to you as an unknown metal. And I'm going to ask you to identify the metal based on the specific heat, which is given to you in a table that looks like this one here. So for example, in this case, the substance, oh, I guess the substance doesn't necessarily match here, but the substance you get on the test will match something like this. So note that these metals all have very low specific heats if you compare it especially to water. Remember, water was 4.184 joules per gram degree Celsius, and here these are all less than 1. So it's much easier to heat up a metal than it is to heat up water, for example. Now, if we get into some common compounds, we have ammonia, for example, ethanol. Now we're in 2.04, 2.46 joules per gram degree Celsius. That's about half as much as it takes to heat up water. Sodium chloride, much less. So it's a very small specific heat. And then water as liquid, of course, is the champion here at 4.184 joules per gram degree Celsius. Okay, now I mentioned before, water is super important. And one reason that we know it's important is not only are our bodies composed of it, the earth itself is composed of a lot of water. We have these giant oceans that we're lucky enough to live close by. So if we have a high specific heat of water, if you have a large mass of water near a coastal city, it'll absorb or release 5 times the energy that's absorbed or released by the same amount of rock near an inland city. So if you're inland and you don't have this ocean water to absorb extra heat, that's why it's a lot cooler on the coast. It's because the water takes up so much energy just to heat up. And so you can think of it as like a heat sink. It's pulling heat into it from the nice, cool coastal cities. Okay, so here's a learning check. This isn't in your notes. This is just kind of like thinking out loud. Like, what's going to happen when ocean water cools? What happens to the air around it? Likewise, thinking about like practical, if you live in the desert, sand in the desert is very hot during the day and it's very cold at night. So what must be the specific heat of sand? I want you to think through these. Go ahead, pause the video if you need to. It's not an sample exercise sheet, but we'll look at the answers here in just a second. Okay, so if ocean water cools, that means that it's giving off heat, right? That's the only way that something can get colder is by giving heat to something else. So the surrounding air has to absorb that heat and it has to get hotter. Sand in the desert, so that doesn't make sense to us, right? On the Pacific, because it's such a cold body of water that it's almost always absorbing heat. So we think of the ocean as cold, but that's not always the case, right? There's warm ocean currents where if you have a warm ocean current hitting a cool place, then the warm ocean current is going to release heat. For example, there's the mid-Atlantic current that releases heat starting from the Caribbean and brings it all the way up to Western Europe. Okay, and then sand in the desert is hot in the day and then it cools down quickly at night. The fact that it cools so quickly at night tells us that it has a low specific heat. In other words, it's easy to heat by the sun and it's easy to cool once the sun goes away. Okay, let's look at some calculations that we'll do using specific heat. If we know the specific heat of a substance, we can rearrange it to give us what's called the heat equation. So I'll just kind of point that out here. We're just going to rearrange the equation that we saw before with specific heat to give us what's called a heat equation. And then what you can do is you can calculate the heat that's lost or gained by a given mass of a substance, depending on how much its temperature changed. So if you have the mass of substance, that's a measurement you can make. You have the temperature change of a substance, that's a measurement you can make. And you know the specific heat of a substance, that's purely based on the identity of the substance. Then all of a sudden, you can calculate the heat in calories or joules that it takes to heat up something by a certain temperature. Okay, so here we go. Sample exercise number 8, using this heat equation. Use the heat equation to calculate the energy in kilojoules that's needed to heat 255 grams of copper from 24 degrees Celsius to 185 degrees Celsius. So just going back here real quick, oftentimes you'll have this heat listed as Q, lowercase q. So it's Q equals M times delta T times the specific heat, SH. Okay, and it says use the heat equation to calculate the energy in kilojoules needed to heat 255 grams of copper from 24 degrees Celsius to 185 degrees Celsius. Okay, so it's asking for the heat, and we know it's this, right? It's going to be Q equals the mass times the change in temperature times the specific heat. And this is what we're looking for. Okay, so look at what we're given. What else are we going to need to look up before we start this problem? Well, the mass is 255 grams, so we're given the mass. We're given an initial temperature and a final temperature here. So we know that the delta T is going to be equal to the final temperature minus the initial temperature. So that's good, we know that. Now, what about the specific heat? Now, we're not literally given the number for the specific heat, but we're told that this is copper. And copper has a definite specific heat. So let's go ahead and look it up real quick. I know it was back here. Oh, yeah, there it is. Okay. We're going to do this in joules. So 0.385 joules per gram degree Celsius. Can you remember that? 0.385 joules per gram degree Celsius. Okay, so that now covers the three things that we need, and now we can calculate the heat. So go ahead. Hopefully, if you knew the answer to this problem or knew how to get there, go ahead, pause the video and finish it up. If not, pause it now, get your answer, and we'll review it here when we come back. Oh, note as well, sorry. It says asks for the answer in kilojoules, so keep that in mind. So go ahead, pause the video. Okay, and we're back. So we did all the things, right? We know that we can calculate the delta T based on 160, it's 185 degrees Celsius as the final temperature, minus 24 degrees Celsius, for a total of 161 degrees Celsius. Okay, we multiply the mass, which we're given, times the delta T, times the specific heat, which we looked up again was 0.385 joules per gram degree Celsius. Okay, so we have 255 grams for the mass, times 161 degrees Celsius for the temperature, change in temperature. Then the specific heat, 0.385 joules per gram degree Celsius. If you follow the units here, check it out. The grams is going to go away because it's grams divided by grams. Degrees Celsius divided by degrees Celsius. That leaves us with joules, which we know we need to convert to kilojoules. Now, normally I would just do this in two steps, right? This is step one and step two. But if you like to do it just in this way where it's all together, that's fine as well. So in this case, joules is going to cancel out with joules, and that gives us our answer in kilojoules. Check your significant figures. It's 3 times 3 times 3. So our answer has to have 3 significant figures. So 15.8 kilojoules. Okay, so that covers when we're heating up a sample in the same state. So if we're heating up liquid water, for example. But now, what about when we have a change of state? So what about when, water boils into steam, or when ice melts into liquid water? So a change of state is when it's converted from one state to another at a constant temperature. So we're going to have 3 different examples here that we probably are familiar with. First off, we have when a solid converts to a liquid, or vice versa, liquid going to a solid. So a substance will melt, is the technical scientific word for it, when it changes from a solid to a liquid at the melting point. Likewise, a liquid will change to a solid state at the freezing point. And in this case, both of them are 0 degrees Celsius for water, right? So your freezing point and your melting point are usually the same. So we call melting and freezing reversible processes, right? The melting takes the solid going to liquid. The freezing takes the liquid and brings it back to the solid. Okay, now one thing to point out here is that in order for you to melt a solid, you need to add heat in. And the opposite is true with a liquid freezing. In order for a liquid to freeze, you have to take heat out. That's the purpose of the freezer, right? When you put the ice in the ice trays and you stick it in the freezer is there pumping heat out of the freezer compartment so that you can remove heat from the liquid, and then that freezes the water into ice. Okay, now this heat is what we call the heat of fusion. That's the energy that must be added to convert exactly 1 gram of solid to 1 gram of liquid at its melting point. So for water, sorry, I gave you the example of freezing, but this is actually heat of fusion is specifically for melting. For water, 334 joules of heat will melt 1 gram of ice at its melting point. So you'd say that the heat of fusion is 334 joules, or 80 calories. If you want to draw it as a chemical equation, which we're not super familiar with how to do just yet, but you can take your water as a solid, turning to water as a liquid, right? That's clearly melting, okay? And then you add in heat to the solid to get to the liquid. Okay, now likewise, I mentioned this before, but heat of fusion is going to be the heat that will be removed or released by the process of 1 gram of a liquid converting to 1 gram of a solid at the freezing point. So again, just in the same way that we had the solid, we added in 334 grams and we got the liquid for water. It's the same for the freezing. It's just that we have to take away that heat instead. So in other words, if we take water, liquid water, and we freeze it at its freezing point, 0 degrees Celsius, then we're going to release 334 joules per every gram of water that is frozen. Okay, so now all of that means that we have heat of fusion. We can use that as a conversion factor. And sure enough, this is something we're going to be doing. So we'll use the heat of fusion as a conversion factor to convert from calories to grams of water, or vice versa. And mostly we'll be using joules for this semester. So if you're calculating the heat that's needed to melt water, then just use this equation here where our heat now, again, we're going to usually abbreviate this as Q, is going to equal the mass of the water times its heat of fusion. We'll put this here for now. It's delta H sub F. Don't worry too much about that. That's something that we'll talk about in the future, but just think of it as heat of fusion. Okay, so here we go. How many kilojoules are needed to melt 32.0 grams of ice at the melting point, 0 degrees Celsius? Now, I think I've explained it well enough that you can give this a try. So go ahead, pause the video here, and when you come back, we will go ahead and go over it. So pause it. All right, and you're back. So let's go ahead and solve the problem. So what are we starting from? Well, we're starting from a certain amount of grams of ice, right? So solid water. And we are supposed to get kilojoules of heat that's needed to melt that amount. So we know that we're going to have to use the heat of fusion. Well, our heat of fusion is given to us. It's 334 joules per 1 gram of water. And this is when we're going from solid to liquid phase. And likewise, our conversion factor, we know that 1 kilojoule is 1,000 joules. So what we're going to do here is basically we have the heat is going to equal the mass times the heat of fusion. So we start from our 32.0 grams of water. We know that our conversion factor here is basically 334 joules per 1 gram of water. And then again, I would stop here normally, but you could also just go directly and convert now from joules to kilojoules. We know that there's 1 kilojoule per 1,000 joules. So we take this number divided by 1,000. That gives us our final answer, 10.7 kilojoules. Check your significant figures. 3 significant figures for the mass of water, 3 significant figures for the heat of fusion. That means our answer should be 3 significant figures. Okay. So melting and freezing are probably pretty straightforward to you. However, there is another type of process that you may not have heard of before, which is what's called sublimation and deposition. So sometimes solids can transition directly from the solid phase to the gas phase. So normally when we think about water, we think about the three states. You've got ice, you melt the ice, you get liquid water. You take the liquid water, then you boil it, you get the gas, so steam basically. But it doesn't have to go that way necessarily. In fact, under some conditions, ice can directly turn into steam in a sense, basically gaseous water in the right conditions. So unfortunately, it doesn't really work for us because these are things that you would see if you grew up in a place with snow. If you ever grew up in a place with snow, sometimes it's snow at night. And then if it's a very dry night out, so the storm comes, it dumps a bunch of snow on you, and it's very dry outside. The snow level will actually decrease when you get these like very dry days. Because what's happening is the solid ice, which is the snow, is sublimating into gas. So you can actually reduce the amount of snow without it melting. Of course, we live in Southern California, so this is not going to apply to any of us. However, there is something that does apply to, which is dry ice. So if you've ever had going back to food, if you ever get the cold treats from some vendor who's maybe at the beach, let's say, and you get the really good kind. It's really, really cold. Those are usually stored on dry ice. And dry ice is solid carbon dioxide. And solid carbon dioxide does not melt under normal conditions. So it is going to go straight from solid carbon dioxide to gaseous carbon dioxide. And those are the chunks of ice that you see that's used to cool things down. It gets really cold. It's about negative 40 degrees Celsius, unlike ice, which is, of course, 0 degrees Celsius. So that's an example of sublimation. Like if you take a chunk of dry ice and just leave it out, it just goes away. Like you'll have a little bit of like condensation left from water that condensed there, but the carbon dioxide itself is just left as a gas. So the particles on the surface of a solid can change directly to a gas. The reverse process is even rarer. It's called deposition. This again, it happens more in like cold places. You can get water will do this, like on your windshield, for example. If you park outside when it's really cold, you can have water vapor particles just deposit directly on your windshield as like ice, and so then you have to scrape it off. It's really annoying. Okay, but yeah, that doesn't really apply much to us. Okay, next up, we have evaporation, boiling, and condensation. Okay, so we know evaporation. Evaporation is when a liquid will, like liquid particles, can turn into gas particles at a temperature that's below the boiling point. So here's an example. We're like slowly heating up a beaker of water, and this beaker of water is about 50 degrees Celsius. Now, if you were to have like a little glass or something here, you would actually be able to collect water particles evaporating directly from the surface. But no, we're not at the boiling point. We're below the boiling point. Similarly, like on a warm day, obviously it's not boiling temperatures, but if you were to like spill your water on the ground, the water is going to evaporate eventually. And this is basically just a process by which individual molecules of water gain enough energy from their surroundings to turn into gas particles, even if all of them don't at the same time. So that's evaporation. Evaporation is liquid turning to gas below the boiling point. At the boiling point, now all of a sudden, we have vaporization, where all of the molecules in here have enough energy now to become a gas. So we see this vigorous bubbling, which indicates the conversion of liquid particles into gaseous particles. So that's why we call it vaporization rather than evaporation. Note that it's just a different process altogether. There's like a few particles on the surface here that are turning into gas, and here it's just from every point in the beaker. Gas particles are liquid particles are turning to gas, and then they're leaving. Then the opposite one is condensation. So this is like if you have a cold, if you have a, let's say you have a glass of ice water. You know that even if you pour it directly very shortly after, it's going to get wet on the outside. And that wet from the outside isn't leaking from inside of the cup. No, it's water molecules from the outside hitting the cold surface of your cup and condensing. In other words, you have these vapor particles that are all around you all the time. That's the humidity that we're always talking about. And you don't see them until they condense onto your cold cup. And yeah, heat is removed. Now, condensation itself, that's an example that I told you already. But when we talk about like this process here, we're going to think about it occurring at the boiling point of water. And basically, it is just like you have this water vapor moving very fast. It's cooled down enough that it loses the kinetic energy, turns into a liquid. Okay, so that brings up our heat of vaporization. The heat of vaporization, very similar to the heat of fusion, only it's now for the transition from liquid to gas or gas to liquid. The heat of vaporization is the amount of heat absorbed to change 1 gram of a liquid to a gas at the boiling point. It's also the amount of energy that's released when 1 gram of gas changes to a liquid at the boiling point. For water, it takes 540 calories or 2,260 joules of heat to convert 1 gram of water to 1 gram of steam. If that seems like a lot, it is. Water molecules really like to be together. So it takes a lot of energy to take them from a liquid phase where they're close together and then pull them apart. Think of like you and your best friend, right? How hard is it to separate you from your best friend? Well, that's the same thing with water molecules here. So the way we would write it in a chemical equation is we'd say it's the liquid water plus this energy, 2,260 joules per gram, to convert it to gaseous water. That's what this G stands for. Okay, the same amount of heat is going to be released when 1 gram of water vapor turns to liquid at 100 degrees Celsius. So it's written this way where we have gaseous water turning to liquid water releases 2,260 joules per gram. So you could call this the heat of condensation as well as the heat of vaporization. Just like the heat of fusion, this can now be used as a conversion factor. We know that for every gram of water that we want to vaporize, we're going to require 2,260 joules of heat. Likewise, every gram of water that we condense, we're going to release 2,260 joules of heat. Just pointing this out here, I totally forgot. Remember, if you, I don't know if you ever worked in a kitchen or anything like that, even if you're just cooking, one of the most dangerous parts of cooking in a kitchen is actually steam above boiling water. So the steam that's above boiling water, if you were to get what's called a steam burn, not only do you have the heat of the steam itself hitting your hand, you also have, when the steam hits your hand, it converts from vapor to liquid. And when it does that, it releases all of this energy here, 2,260 joules per gram. Tremendous amount of heat, and it is extremely painful and can cause like very severe burns. So do be careful if you ever work in a location that has steam. Like for nurses, you may work with like an autoclave system. And an autoclave system basically has this high, I think usually it's steam that they use to clean things and basically get rid of all the biological components of different tools or PPE, for example. And you have to be careful when you release the autoclave. Of course, it shouldn't let you if it's dangerous, but always be aware of anything that uses steam because that can cause very severe burns. Okay, so bringing it back, how many kilojoules are released when 50.0 grams of steam from a volcano, I guess it could be from anything, but from a volcano, condenses at 100 degrees Celsius? So go ahead, give this one a shot. Again, pause the video, solve it out, and then come back with the answer when you're ready. Go ahead, give it a shot. All right, so no surprises here. We're given our grams of steam, and we need the kilojoules released. So that means we need to use the heat of condensation, figure out the joules that were released by that many grams of steam. So given that we have 50.0 grams of steam, we want the amount of energy that's released. Well, then we need this conversion factor here where we have 2,260 joules for every 1 gram of water. And that's going to give us the heat that's released in joules. Now, on the other hand, it's asking for kilojoules eventually. So we know that we'll then convert that joules to kilojoules using this conversion factor. Set up the problem. It's 50.0 grams of water, and there's 2,260 joules per 1 gram of water. Convert it to kilograms and check your significant figures. 3 significant figures for the mass, 3 for the specific heat. The heat of condensation, and that gives us 3 significant figures for answer, which should be 113 kilojoules. Okay, all right. So now, with all of this knowledge, right, we know the heat of vaporization, we know the heat of fusion, we know as well how to use the specific heat to figure out the amount of heat that it takes to increase the temperature of a liquid, solid, or gas. Well, now we can actually draw a very useful diagram, which is called a heating curve. The heating curve basically shows the change in temperature for a physical state, and then also a heat added. So the x-axis here, think of it as the heat added, and you're starting from 0, and you're going basically slowly adding heat. And as we go, as we increase the amount of heat that's added, we're going to change from a solid to a liquid to a gas. And the other thing that's going to change is the temperature. So we start from a solid, right? The coldest example of any substance is always going to be a solid. Now, as we add in heat in the solid form, the solid heats up until you hit the melting point. Now at the melting point, you're going to have to add in energy, heat, basically, until you melt all of that solid. So we have this solid heating phase, then the melting phase. Then we're at a liquid phase. Well, now, as we add in heat, the temperature is going to increase according to the specific heat. So the liquid phase, basically, you have an increase in heat, right? You're adding in heat, and that increases the temperature until the boiling point. Well, for water, that's at 100 degrees Celsius. Once we hit 100 degrees Celsius, now we're going to add in more heat until all of those particles are converted to a gas. This is the heat of vaporization. And then, of course, once we're at a gas, then we add in more heat, and that just goes on forever, basically. A cooling curve is the opposite. Basically, you can think of it, I honestly don't use cooling curves. I just think about going the opposite way on a heating curve, but this works fine. So on a cooling curve, you're going to start from, whatever position you want. If I say, okay, you have steam at 140 degrees Celsius, how much heat is it going to release if you take it to ice at -20 degrees Celsius? Well, let's look at the different links that happen here. First off, steam can cool from 140 to 100 degrees Celsius. That'll release a certain amount of heat according to the specific heat of steam. Then that water is going to condense. And we know that condensation is going to release a certain amount of heat as well, according to the heat of condensation. Next up, the liquid water, now is going to cool from the boiling point to the freezing point. We know that that's going to release a certain amount of heat as well. Then we have the freezing point. So we freeze the liquid water into ice. That also releases heat according to fusion. And then finally, we cool down the ice, and that is also going to release heat as it is. So in the cooling curve, that's going to show us the heat that's removed or the heat that's released by the process. Okay, so checking in on what we understand about this heating curve. You may want to kind of watch that a couple times, and hopefully it makes sense. But our questions here are, a plateau on a heating curve is going to represent what? And then a sloped line on a heating curve represents what? Go ahead, pause the video. You can even go back if you want to. Give it a second to think about it. And when you come back, we'll look at the answers here. Remember, this is what a heating curve looks like. Okay, so a plateau is actually represents, this is kind of a trick question. I should have told you there's two possible answers here. A plateau on a heating curve represents a constant temperature, that's true, but it also represents a change of state. Those are when we're going from solid to liquid or from liquid to gas. And sure enough, it's at a constant temperature, melting point or boiling point, respectively. And then finally, a slope line represents a temperature change. Okay, all right. Using the cooling curve of water, answer each of the following. So this should be in your handout. So just get a sample exercise number 12, and we'll go back here to the cooling curve. Okay, go ahead, pause the video here, answer those questions. And when I come back, we will have the answers to look at. So pause. Okay, so we know that water condenses at a temperature of 100 degrees Celsius. That's its boiling point or condensation point, either way. At a temperature of 0 degrees Celsius, liquid water freezes. Okay, no trick there. At 40 degrees Celsius, water is a liquid. And then finally, when water freezes, heat is removed. In other words, you're taking away heat to go from a liquid to a solid. Okay, all right, now this is the big one, right? So this is going to be a question that you're going to see on your exam again. And let's go ahead and take a look at what this question says, and then we'll solve it together. This one's tricky, so I really want you to give it a shot and think it through, and then we'll show you kind of how you want to construct this with the answer here. So, okay, it's a 175 gram sample of steam, and it's emitted from a volcano, again, at 100 degrees Celsius, excuse me. It condenses, it cools, and it falls as snow at 0 degrees Celsius. So how many kilojoules were released in this process? So think through. So go ahead, pause the video now if you're pretty confident about how you're going to solve it. And then I'll give you another hint, then one more hint, and then I'll show you how to answer the problem. Okay, so first hint is this. You have a sample of steam, and it condenses, cools, and falls as snow at 0 degrees Celsius. So how many different things happen to this steam before it can be snow? And basically that's going to tell us how many calculations that we have to do for this problem. Okay, well, it's at 100 degrees Celsius and it's steam, right? So we know it's going to condense from steam to liquid. So that's step one. Here, we'll just put this here. So we'll call it Q1. We know that the first process is condensation. Right, we're going to go from a gas to a liquid. Q2. Next up, as a liquid, it has to go from 100 degrees Celsius, the boiling point of water, to 0 degrees Celsius, the freezing point of water. So we're going to cool liquid water from, and we'll just put this here, from 100 degrees Celsius to 0 degrees Celsius. And we'll just put 100.0 here, just to be fair, because I think it's going to screw with your significant figures otherwise. Okay, then what happens? Well, now we have liquid water at 0 degrees Celsius, but that's not what it's saying. It's saying we have snow, and snow is ice. So next up, we have to freeze that water. So there's 3 separate processes that are going on here. Okay, now the next hint is going to be, how do you figure out the total amount of heat that was released? Well, the total heat, and again, I'm using Q here for heat, is going to equal the sum of the 3 processes. So Q1 plus Q2 plus Q3. All right, give it a shot. And we're going to go through the answer on the next slide. But hopefully this kind of gave you the hint in the right direction. So for those of you who didn't take the, or who took the hint now, go ahead, pause the video and work it through. When you come back, we will have the answer. Okay, here we go. Step 1. We know that we already said this, right? We have 175 grams of steam at 100 degrees Celsius. We need the total heat that was released when we condense the steam at 100 degrees Celsius. Then we cool the liquid water to 0 degrees Celsius, and then finally we freeze it to snow. So we need the heat of condensation. We need the specific heat of liquid water, and we need the heat of fusion for water. Well, fortunately, we're able to do all of those things. We can also set up a cooling curve that'll determine the kilojoules that are released. This is just another way of visualizing the process that we talked about, right? This is Q1, this is Q2, and this is Q3. Okay, so first up, step 1. We know that to take 1 gram of water from the gas state to the liquid state, it takes 2,260 joules, or releases, excuse me, 2,260 joules. So our conversion factor there is 2,260 joules per gram. Likewise, we know the specific heat of water is 4.184 joules per gram times degrees Celsius. And finally, we know that it takes 334 joules, 334 joules are released from 1 gram of water turning from liquid to solid. So that's how we can actually do this. So we have, first up, for the first part, we take our 175 grams of water and we use the heat of condensation to figure out that, sure enough, 396 kilojoules would be released. Okay, next up, we're going to do the specific heat. It's 100 degrees Celsius minus 0.0. That gives us 100 degrees Celsius with the decimal here. That's our temperature change. Now we can use the specific heat to determine the amount of heat that's released from cooling the water. So that's 175 times 100 times 4.184. Convert it to kilojoules, and that gives you 73.2 kilojoules. Finally, the heat that's released from the liquid freezing, well, that's our heat of fusion, right? So that's 175 grams, again, times 334 joules per 1 gram, converted to kilojoules, and that's 58.5 kilojoules. Okay, so all we have to do now is add it all together. We got 396 plus 73.2 plus 58.5. The correct answer at the end should be 528. So, and again, check your rules here. We know this one to the ones digit, the tenths digit, and the tenths digit. We have to round our answer to the ones digit. Okay, wow. Well, that does it for chapter 3. Make sure to get a good start on the homework and get that done. I already mentioned, I gave you kind of 2 hints as to what's going to be on the exam. 2 of my favorite questions are from here, including this last one here. Go ahead and give it a shot. And if you have any questions, of course, ask in the comments down below. And I will be getting back to you as soon as I can. But that does it for chapter 3. I'll see you very soon, and we'll come back soon with chapter 4. All right, bye-bye.